Okay, here's the third PowerPoint in the refraction section. This is the third attempt at recording it because one of my kids just knocked something off the wall while they were playing darts and there was an almighty crash, so I had to stop and start again. So here's the list of what's in this PowerPoint. So we've got what is total internal reflection, what's critical angle mean, and how to work that out, basically, and do some calculations with it. So first bit is just a basic recap of refraction that we've already gone through. So the light is, in this case, is bending or refracting towards the normal as it goes into the glass, because it's going into a medium that is more dense. And then when it comes out of the glass, it's going to bend or refract away from the normal. What you're then looking at is what happens if we change that angle of incidence. So if we make that angle of incidence bigger, then that refracted ray that's coming out is going to gradually start getting closer to that boundary between the glass and the air that's at 90 degrees to the normal. So if we make the angle big enough to the point where the light then goes at 90 degrees to the normal, which in this case is just along the edge of the block because it's a rectangular block, that point there, that angle of the angle of incidence at which that happens is called the critical angle. If you then make the angle bigger than the critical angle, so if you keep increasing that angle of incidence, then what happens is the light then reflects back into the block rather than coming through it. So then you get what's called total internal reflection. Okay, so the diagrams below are showing that. So to start with, if the angle of incidence is less than the critical angle, most of the light will be refracted, but you might remember just from seeing it yourself when you've done it that you do always get, or often get, a little bit reflected back. If you get it to be exactly at the critical angle, the majority of the light will refract along the boundary at 90 degrees. Again, you get a little bit of reflection. And as soon as you get above that angle, then you get no refraction at all, and you get total internal reflection. So all the light is reflected internally. Where this is used, fibre optics are the main thing. So fibre optics are used for communications mainly. So communicating, they can send huge amounts of data digitally using light waves essentially through the cables, and you get lots and lots of cables. When we get back to school, I'll show you one of a fibre optic cable because we do have one in school that I can show you if you remind me. So that's using the principle of total internal reflection by looking at this basically. So the light is going through a glass core, which is then got another cladding of glass with a different a lower refractive index in the core. There is also often a reflective coating on that cladding as well. So just in case any of the light does, if it doesn't quite hit at the right angle, so you might get a reflective, like a silver coating on it as well to send some of it back. That'll be on the sort of the outside of that cladding layer. So the angle that the light goes in, because of the two different refractive indexes, basically ensures that each time the light hits the edge of the core, it reflects back rather than going through it, and that keeps doing it over and over again. It's very, very thin, so it's flexible. So you can bend them, you can move it, but as you can see from that diagram, you generally get lots and lots of them within one cable. The one that we've got at school is probably a good 4 inches, 3 or 4 inches across, and it's got loads of fibre inside it. Okay, so that's the main use. Diamonds are often mentioned. Diamond is the material that's got the lowest critical angle. So it's got a critical angle of 24.4 degrees. Just as comparison, glass is about 42 degrees. So diamond's only 24.4. And what that means is that most of the light, or certainly a lot more of the light, is going to strike the diamond at an angle of greater than that 24.4, which means it then ends up being reflected inside. So because it's then reflecting inside, bouncing off all that inside, and then obviously some of it is refracted as well, then you got that combination of both, which then makes it nice and sparkly. So looking at how these two things link, so the critical angle We just said that diamond's got a critical angle of 24.4 and glass has got a critical angle of 42, and perspex is pretty similar to glass. Then it's obviously not the same for everything. So it's not the same for everything because everything has a different refractive index. The amount of refraction that happens is related to the critical angle, because the more it refracts, the quicker it's going to get to that point where it's going to then come back and reflect rather than refract. So at the critical angle, your refracted ray is 90 degrees. So that means that sine theta 2 is sine 90. Okay, so in this case, what you've just got to watch is that in this case, N2 is air, not N1, because you're looking at the ray already inside the block and what happens when it comes out of the block. So you have to, at this point, N2 is the one that is 1, sorry about that, and because that's air, and N1 is the refractive index inside the block. Okay, so N2 over N1 is equal to sine theta 1 over sine theta 2, so that's just our Snell's law. Stick the numbers in, so we've got 1 over N1 is equal to sine theta, and we've just changed it to C rather than 1, because we're looking at the point at which it's the critical angle divided by sine of 90. Rearrange that, and we end up with with N equals 1 over sine of the critical angle. So that we can then work out the refractive index. So if we know the critical angle, we can work out the refractive index and vice versa. So for example, critical angle of diamond is 24.4. So what's the refractive index? So we're just doing N equals 1 over sine theta C. So N is 1 over 24.4. 1 over sine 24.4, which then works out at 2.42. Okay. Now here's another one. Now this one's quite complicated, and I haven't seen an exam question like this before. I'm pretty sure that we did this in class, because I seem to remember you guys talking about Z angles and things, and it's much more of a maths problem than it is anything else. I haven't done it using Z angles, but I've gone through it the way I know how to do it. But I seem to remember you confusing Miss Baxter a little bit as we went through it, and you were just basically using your math skills. So what this one is basically saying is what happens to the light as it goes into these prisms. So we've got one where it's going in on an angle, and one where it's going straight through at 90 degrees on the vertical side. So here's the first one. So the bit in pencil is just what's in the picture, basically. And I've just realised that is wrong. Oh, the calculation's right, but what I've written is wrong. So where it says 60 degrees in red, that should say 30. So the angle, those two angles are supposed to obviously add up to 90. So that I should have written 30 there. I've used 30 in the calculation, I've just written it wrong at that point there. So it didn't give us the angle between the ray of light and the normal, so you have to work out what that is first, which obviously should be 30 degrees. Then I've just used the fact that I know that the refractive index of glass or perspex, whatever it was it said in the question, glass is about 1.54. Stuck that into the Snell's law formula, and I've ended up with an angle on the inside of 18.9 degrees. What we need to then do next is work out if that one's 18.9 degrees. What I've then done is I've worked out the angle on the inside of the triangle, because I want to know all of the angles of the triangle to work out what the angle is going to be at the other side, the right hand side of the triangle. So if that one with the first question mark, the one that I've just worked out, is 18.9, then the other one must be 71.1, because it's just 90 take away 18.9. If I know that that one's 71.1 and I know that the top one is 30, then the bottom right hand angle must therefore be 78.9 degrees. If I know that that's 78.9 degrees, I can then work out what the angle of incidence is, because it's just going to be 90 take away that. So that's there. So that's 11.1 degrees. That's 11.1 degrees. That is less than the critical angle. So therefore, the light will refract and just come out of the block. If I wanted to, I could work out what the angle of refraction was as well, just using Snell's law. So that one, that'll refract. And the second one, so that was the second one, it's going straight in at 90 degrees to that side, which means it doesn't change direction. It's going to go straight through and it's going to hit the hypotenuse of that triangle. Working out the angles, if we've got an angle, a 90 degree right angle, a 60 degree angle, the other angle must be 30, which means then the angle of incidence, just the other side of that one, must be 60. So if that's 60 degrees, 60 degrees is more than the, hang on, just move that down, hide that for a second. 60 degrees is more than the critical angle, so that means that the light will reflect. So we'll get total internal reflection and not any refraction. It'll reflect at an angle also of 60 degrees, which will then bring it down, not straight down, but bring it down to the bottom left-hand side of the screen. But what I realised after I had drawn it out, and I couldn't be bothered to draw it again, is I've just made one slight mistake in that when the light comes back out of the prism again, it'll refract. So I've drawn it coming straight out of the prism, but it won't because it's hitting that bottom side of the triangle at an angle. So it will actually refract slightly and come slightly more down the way, basically, as it comes. So that last little bit of it's wrong. But the rest of it's right. Okay, so that's it on total internal, the critical angle stuff and total internal reflection. So now you need to do questions 8 to 11 on page 30 in your booklet. Again, you may have done some of these before, but again, it will not do you any harm to do them again. And after that, can you do the sheet that is called Homework 24 on refraction? And can you send those answers to me, please? Okay.